recording, it's rolling. It's Thursday, January 22nd. So here's top math edition. So I'm Module 7, off the job to make the list. Okay, so I did do quiz makeups today. So I will get these quiz back to you, of course, as soon as I can. But everybody's gotta take it first, and that's for a few classes. So yesterday, I told you guys how logarithms work. Actually, I got some notes right in front of me here. Right, so here's how you can express an exponential as a logarithm, right? Vice versa, you go back and forth, right? And once you do that, here's some interesting properties of logarithms you can do with equations. Okay, so I took you through briefly through some examples, but what we do today is we're gonna go through the book. I'm gonna solve a bunch of these with you guys. You guys take notes. So take notes today, and then I'll have you guys turn your notes in at the end of class, and I'll give you guys some class points. Yay! So do that. Love those. Yeah, notes and points. All right. All right. So I showed you guys how these worked yesterday. So I'm just gonna jump in and start solving these. Yeah, let's see where this adventure goes here. All right. So all these green highlighted ones, I did have them a longer video. So I'll pick some of the other ones. So you guys have opportunities to see some other things too. I mean, I might do some green highlights. You know, but it's a good example. All right. So I'm in section 8.1. This is on page 59. If you have your book, if you want to follow along. Okay. Right, so let's go down the list here. So number 2. Okay. Right, so number 2, they give you this log base 3 of 1 over 27, and that's equal to negative 3. Well, supposedly that's true. Maybe we'll take their word for it now. Actually, I can show you guys how to test that. Okay. But what they want you to do here is to write this in exponential form. Right? Write this in exponential form. Right. So they want you to go from basically this box to this box. So go ahead. Right. How would you guys write that in exponential form? No, you guys write your name on your paper? Oh, yeah. Right, so when you eventually turn this in the class, right, they give you points. Okay. Right. So they give you this. Right, so you take this base, which in this case is 3. You guys see base 3 here? Okay. And write that to the power of the other side, which in this case is negative 3. Okay. And that's equal to the sum side piece, which is 1 over 27. Okay. So this are the same expressions, just written different ways. One's a logarithm, one's an exponent. Okay. Guys, is this true? Is 3 to the negative 3 1 over 27? Yes. Yeah. It is, right? Because I know 3 times 3 times 3 is 27, and the negative power makes it reciprocal, so whenever. So that would be true, wouldn't it? Okay. And I'll show you another way you can also check this from the logarithm statement. Okay. And it's one of the last things I showed you guys yesterday. Guys, remember if you have some weird base, like log base b to be anything, in this case maybe 3. Okay. You can convert bases by using this line right here. So let's try it. So if this is true, maybe I can take natural log, for example, of 1 over 27, okay, and then divide that by natural log of 3. Okay, that should be equal to what? See if you guys are following. Negative 3. Yeah, negative 3. Okay. Now I'll put a little question mark here because we're going to punch this in the calculator and see if this is actually true. All right, so do open parenthesis. Do you guys see the ln key for natural log? All right, hit that. And then 1 over 27, close, divide by, and then natural log of 3. Okay. As long as this says negative 3, then these are true statements. All these log rules are working. Yeah, there it is. Okay, just like that.
Calculator. Oh, we can't see behind the calculator.
All right.
Yeah. Jake was too scared to ask.
I never even said anything.
All right, it's working out for you guys.
That's your case, Jake. You don't have
Yeah,
to
you're
get
sucking on my head.
No, that's not.
But you're trying to suck on my head, what? Kind of weird call me good.
All right, let's try another one of these. Number 5. So log base 4 of 64 is equal to 3. Right? Now you're just supposed to write this as an exponent, right? Which would last ones like that. Okay. All right. Guys, how can you write this as an exponent?
You can't. Okay.
3 to the power of 4 equals 64.
Oh, take this base 4.
Or 4 to the power of 3.
Yeah, to the power of 3 equals 64. Right. No, that's definitely true, isn't it? Because 4 times 4 times 4, that would be 64.
Wow.
Right, and let's do that base conversion trick that I showed you guys before. Okay. So what's another way to look at this? what if you do natural log of 64 divided by natural log of what? What am I gonna write right here?
4.
Yeah, 4. Okay. And if this is all true, this should be equal to what?
3.
Yeah, should be equal to 3. Okay. So calculator,
Good job, Todd.
let's do natural log 64 divided by natural log 3. Whoops. Natural log 4.
I see something.
All right, that is 3. Check. It's all good.
That's good.
All
Why
right.
did you cause talking to you?
All right. Example 2.
Maybe.
Hey, can you go the other way?
Now,
Like, if they give you the exponential form, can you turn this into a logarithm? Ooh. So number 8, let's look at. So
What'd you
3
say?
to the negative 4 equals 1 over 81. Oh, first of all, is that a true statement?
yes.
Yes. Because guys, what is 3 times 3 times 3 times 3?
Oh,
That is 81. And then the negative power makes it reciprocal. Okay, so that checks out, right?
We are.
Okay. And now how can you write this as a logarithm?
Jacob's log.
Yeah, there you go. Log base 3. Log base 3 of what?
1 over
1 over 81?
Yeah.
And that should equal what? Yeah, negative 4. There you go. All right. And let's check that. Or, so this is the answer they're looking for. Okay. But let's check that with the base conversion. So what if I do natural log of 1 over 81? And then I divide that by natural log of, what am I going to write right here? 3. Okay. And basically, if that equals to negative 4, we're going to find out. If it is, this is all on track. So natural log of 1 on 81 and divide by natural log of 3. Yep, that's negative 4. Checks out. Bing. It works.
not good.
I thought it was kind of fun.
No, man, change that.
Alright, so you guys got this big score?
What was that?
Yes.
Is good? Alright, let's try another one of those.
It's just a.
So number 11. 11
show.
It says 2 to the power of 9 is equal to 512.
What?
So how can you write this as a logarithm? Log base what? Yeah, base 2 of what? 512? And that should be equal to what? 9? Not sure? And it matches. Okay. Now let's do the base conversion trick and see if that checks out. So what if I do natural log of 512 divided by natural log of what? Look up right here. 2? Okay. And if this works out, this should be equal to what? Should be 9? Okay. Let's see if that's true. Is that true? So I do natural log of 512 divided by natural log of 2. Yeah, it is 9. Check. Bing. What's that? We are 4 for 4. Right, you guys doing good?
Yeah, I watched that.
Yeah. All right.
Sit next to my mom.
Next section. Let's do one of these. How about number 17? That looks fun. 17. Log base 4 of 1 over 32. Okay, so what is that? Can you solve that?
You're young, you don't really.
Yeah, I wasn't supposed to.
I know, I was new.
Actually, this is going to be a weird one.
Actually.
That's okay. We'll do this one. We'll do another one in the section. Okay. Guys, how do you think you could solve this?
Natural log and then find the answer so you can finish.
Yeah. Okay. Yeah, you could do that trick we did. Yeah, you could do natural log 1 over 32 divided by natural log of 4. You could. That should be the answer. Okay. Let's see what it says. Natural log 1 on 32 divided by natural log of 4. Yeah, it says it's negative 2.5. So that should be the answer, shouldn't it?
Yeah.
Negative 2.5? Right. Now let's solve this a different way. It's because we've solved each one of these so far 2 different ways. Okay? So here's another way to think of this. Guys, could I set this all equal to x and basically you're solving for x? Isn't that true?
Yeah.
Solve for x? Okay. So now that it's equal to x, can you rewrite this as an exponent and think of it in terms of exponents? How can you write this as an exponent? 4 to the what? 4 to the x equals what?
1 over 32.
1 over 32. Okay. Now, here's where it's a little weird. 4 and 32 have what in common? Yeah, 2. Yeah, it's 2 decimal power, isn't it? Okay. So isn't 4 like 2 squared? Okay, so now I'm going kind of back to model 7 type thinking, right? Just to I'll also get to this answer, right? Okay.
Yeah.
And 32, guys, that's 2 to the what?
Just names kid.
2, 4, 8, 16, 32.
What?
Huh? 2 to the left.
Six.
Negative 5.
Oh, I
Right? Negative because it's a reciprocal, and then 2 to the 5 is 32. Okay. There. So, do you guys see what the next step would be from this perspective? 2x is equal to negative 5. You guys see that? Because they share the same base, too.
Yeah.
So I think 2x has to be negative 5. So x has to be negative 5 over 2, which is negative 2.5, which is exactly what the calculator said just a couple minutes ago. Same thing? All right. Okay, that one's going to have to be a fraction. Let me do a non-fraction type answer. I think number 15 is going to work out as a whole number. Let's see, 15. Log base 5 of 625. Here, I'm going to say that's equal to x, and let's solve for x. Let's turn this into an exponential and solve it. So how could you make this in? Here, guys, how can you write this as an exponent? Yeah, 5 to the x. That's equal to
625.
625. Right. And I bet this you can solve. Because guys, how many times do you multiply 5 by itself to get to 625?
4.
Yeah, 4. X is 4.
Oh yeah, now you
Okay.
this.
Right. Or let's go back to the beginning. Let's do the base conversion. So guys, can I do natural log of 625 divided by natural log of what? Huh? Yeah, 5. Okay. That should also equal x, which should be 4. Let's see if it is. So natural log 625 divided by natural log 5. Yeah, it is 4. Check. All right, you guys good? All right, so that's real basic log and exponent operations. Right. Let's hit one of these story examples. Number 23. 23. Because it looks like I did 22 on a separate video. You can always go look at that. That's fine. Okay. So 23. Value of a guitar in dollars after X years can be modeled by this equation. So say Y equals G times 1.0065 to the power of X, where G is the initial cost of the guitar. So I'll go ahead and label it. Initial cost. Looks like Y is the value after X years, and X is the number of years that has passed. Okay. So you guys get with that equation in the context. Okay. Actually, speaking of the context, okay, guys, does this look sort of like like continuous compounding interest rates? Does it sort of look like that? Right? Right. Like guys, if G took the place of principal, then what would the interest rate be for the same equation? What's the interest rate sort of?
Like 0.65%.
Exactly, 0.65%. Right. Or in this case, maybe you could say the growth rate and value of the guitar. Right. So I'll say well, I'll just put this in parentheses. R equals 0.65%. It's less than 1%. You guys see it less than 1%? Okay. All right. Anyway, that's just a little side thought. Okay. But what do they want us to do here? If the guitar costs $400, maybe that's the initial. Yeah. Okay, that's the initial cost. Okay. So we're gonna let this initial cost be $400, right there. Okay. Then write an equation to find the number of years it takes the guitar to reach any particular certain value. Okay. So we're going to replace G with $400. That's good. Okay. We've got X number of years, and Y is the value after so many years. Okay. Guys, what did it just ask us to solve for? X or Y? X. Yeah. Okay. Now, the particular value they left open. So maybe you want this to double in value to $800 or whatever. Right? You can make Y anything. And we'd have to say, well, how many years would it take for that to happen? Right? You guys got the premise?
Mhm.
Right? No, this is one where, well, the numbers aren't like nice numbers but from module 7. So you actually legitimately do have to use a logarithm to solve this. Okay? And so can you guys write a logarithm version of that? How can you turn that into a logarithm? So saying y is equal to $400 times 1.0065 to the power of x. Right, we're solving for x ultimately. Okay. Guys, what's a good first step? Actually, there's a couple of ways to start this off. What do you guys feel like doing first? Solve for x.
Make y 1,000.
Well, we're gonna leave y as just a variable, right? So that y can sort of be anything, right? Like, what's the value of the guitar in the future? Well, maybe 1, 2, 3, 4, 5 years from now, it might be worth a lot of different things. We'll just leave y as y. Right? We're gonna get x in terms of y. How about this, guys? Could you divide the 400 down? Would that possibly get you a little closer? Okay, that's one way to kickstart the algebra. So I can do y over 400. I'll just drop the dollar sign. You guys know this is all going to be dollars, okay? And x is going to be in years. So 1.0065 to the power of x. Okay, but now see what you're solving for is stuck in the exponent. So how do you get it out of the exponent? You have to apply a what? Logarithm. Logarithm. Guys, can I take a logarithm of both sides? Okay. In fact, there's a couple ways you can do this. You can use this weird base right here. Actually, let's do that first. Right, that's probably what your book intends, but all right, let's try. Okay, so because you could go log with this weird base 1.0065 okay, of y on 400, and that's equal to what? X. Yeah, equal to x. Okay. Okay. Which is probably what your book is looking for. Okay. Now, I do want to show you guys what this looks like in Desmos. I can do that. There's other things I want to do with this too. But let's take a look here. I'm going to slide this up. You guys can see its equation. See right there. Okay. And also, here, guys, I'm going to switch what's x and what's y. Is that okay? Like, okay, so I'll say y equals, but really you guys know that's x from the paper, right? Okay. So I'll do log. Now if I do underscore, it lets me type the base. So 1.0065. Okay. And then that's the value over 400. Okay. Like this. Okay. Now I know we're talking about say price values of $400 or more, right? Hey, doesn't that look like basically one of those logarithm curves that you guys saw yesterday? Right? Like I know the number of years that passes has to be, yeah, I would say that. Has to be 400 0. So okay, so you guys see that coordinate 400 0. Right, so for a $400 price, 0 years have passed, right? Because that's the initial price of the guitar, right? The value can only be positive, right? So the value of guitar can only be positive after that, right? Hence the domain restriction, right? And then is what if the question was how much time does it take to double, for example? Can I set up another equation and say here since the sort of x coordinate on the graph is the price. Okay. What if I let that go to 800? Okay, something like that. Okay. How much time would that take? And guys, you see it right there. You guys see that coordinate? 800 comma 107 it rounds to. Okay. What does the 107 mean? Takes 107 what? Years. Takes 107 years for the price to double. Okay. Is that? Okay. Now, there's maybe a cleaner way you could write this equation, but which would result in the exact same graph. Okay, let's do the log from the base conversion. So I could do natural log of y over 400 divided by natural log of 1.0065. Okay, that's also equal to how much time it takes to reach a price of like Y dollars or something. With that. Okay. So actually, either one of these would be okay. They're the exact same graph. Okay, you guys good there? Okay. And then if you swapped out the story for like the price of something, so increasing over time, right? Yeah, because you could turn this into a bank account question. And you can say like, how many years does it take for my investment to double or whatever? Okay. Same math. All right. Ooh. Then we should make some graphs down here. So let's do 20. Let's do 27. So let's do what this looks like. They give you f of x equals log base 8 of x. Okay. All right, so I think it's probably a good idea to make a table, like an XY table. Let's pick some X values and Y values that maybe we could run. Okay. And plot this on a graph. Okay. Now you guys saw some log graphs yesterday and also today. Right? You guys know they take this hook type shape with a vertical asymptote normally, right? Or like logarithms. Okay. So we can come up with some X and Y values. Okay. And one way you could do this, because in place of f of x, I could just call that Y. Call that Y. Okay. And then you could turn this into an exponential. How could you rearrange this and turn this into an exponential? What to the power what is equal to what?
You're so gay.
Oh.
Huh?
You think so?
Guys, what's the base?
You
8.
think so?
So right, 8 to the power of what?
I think so.
To the power of y is equal to x. Right. Guys, this equation right here, and this equation right here are the exact same equation. Just one's a logarithm and one's in terms of an exponential. The same thing. Okay. So now the exponential I know I'm more familiar with from module 7. Right? Like I can definitely come up with some y values. Like how about -1, 0, 1, 2, how about something like that. Okay. Guys, if these are your y values, now we're plugging in y and we're solving for x. Okay, I'm looking at this exponential. Okay. Guys, what is 8 to the -1?
Oh man,
Yeah, 1 over 8. What is 8 to the 0?
1.
1. Okay. You can plug this in your calculator. Okay. Just make it a table. Okay. Guys, what is 8 to the power of 1? 8. And what is 8 squared? 64. Something like that. Okay. Now, you could have gone the other way. Like, if you never crafted the exponential equation, what if you left it in log form? Okay. Guys, let's try this. Log base 8 of each of these x values should produce this y value. Okay. And if you push it through that base conversion, can I do this? Can I do natural log of 8 divided by, or natural log of x in it divided by natural log of 8? Okay. That should be the exact same thing. So let's try this. So you guys got your calculators? Calculator? Okay. So let's punch in this right here. Do natural log. And then, well, supposedly this table of values works, but we're going to find out. So type 1 over 8. We'll test the first one. Okay. Close parentheses, then divide by natural log of 8. Okay. And guys, if this is all correct, when I hit enter, what should my calculator say? Yeah, -1. It's got to say -1. And it is -1. You guys see it? Okay. Let's test one more of these. So natural log of, here, maybe I'll pick, how about 64t? So if I do 64 divided by natural log of 8, I should get 2. And it is 2. Yeah. All right. So you guys got it? All right, let's plot this. All right, so I see all my x values are positive. They go up to 64. So maybe I'll scale this. Go 10, 20, 30, 40, 50, 60, 70. Okay. And then the y values, well, they don't go that far. Okay. And that typically is the case with logarithms. So let's go -1, 0, 1, 2. Okay.
Oh, yeah.
Like that.
All
Right, and then let's plot all these points. So when x is 1/8, y is -1, that's like right here. Bam. I mean, it's pretty close. When x is 1, y is 0, that's bam, right about there. 8, 1, just bam, right about there. And then 64, 2 is like way over here. Okay. You guys see this is going to be a really extreme hook, like this. Gosh, like that. Yeah, and that looks like that log graph that I plotted earlier today and also yesterday. Okay. Don't log graphs look basically like that? Okay. Okay. And again, while you guys are finishing writing this one in your notes that you're going to turn in, is oftentimes scenarios that involve logarithms are we're discussing like orders of magnitudes of things. The example I did yesterday with you guys was earthquake Richter scale readings. They go from a magnitude 5 to a magnitude 6. Right? That's like 10 times the intensity. Right? So on this log graph, say if this represented an earthquake somehow, right? If you do 10 times the intensity to the right, you guys see how the Richter scale rating would be the y-axis and it only goes up a little bit at a time, maybe from a 5 to a 6. What's that? All right. So one more thing. It said identify key features. So you guys see there's going to be a vertical asymptote. I just went ahead and dashed it. It's the y-axis is the vertical asymptote, which is at x equals 0. All right. Keep going. Let's do down here 47 biology. Biology 47. Okay. This earthquakes, this investing, and also this pH looks like a did in another video if you want more examples. So 47 biology. An amoeba divides into 2 amoebas every hour. The number of amoebas after T hours can be represented by P equals log base 2 of n. Okay. Again, n represents the number of.
I think of one more these.
I don't know. You look for.
Yeah, but you're in the same thing. I'm gonna send it.
Amoebas. And T represents the time in hours. Time in hours. All right. Okay. So you guys go with that premise there.
All right.
What's the wants to do? Graph the function. Look at domain and range. There's a couple follow-up questions, but let's start with that. Perfect graph. So let's make a XY table. Except instead of XY, maybe I'll call it T and N. Okay. And then of course we'll make the graph. Okay. And time is going to be positive. It's the number of amoebas also going to be positive, right? Yeah. Right. Now, here, how's actually, you know what? Maybe I should swap these columns. Let me do that. Let me swap N and T. Let me put T over here and N over here. Okay. Reason being, because the fact this is a log graph, looks like the number of amoebas is going to go on the x-axis, and how much time has passed, we'll consider the y-axis, right? Like a version of the story could be, let's say you have some initial number of amoebas in a petri dish, right? And come back sometime later. Oh wait, how much time has passed? Has it been 1 day, 2 days, 3 days? I kind of forgot to label this one. But you look at it and see how many amoebas are there. And because you have a count of how many amoebas and you know how they grow, you can calculate how much time has passed. That's could be exactly what this equation is, right? So let's rearrange this as an exponent, kind of like we did for the last one. Guys, how can you write this as an exponential equation? 2 to the what? T equals n. Yeah, so you can do that. Okay. And then I think it's probably easier to make a table of values. So let's go time is, how about 0, 1, 2, 3. Yeah, let's do that. 0, 1, 2, 3. Okay, so guys, if 0 hours have passed, then how many amoebas are there?
1.
What's, yeah, 1. Okay. How about 1 hour's passed? How many?
2.
2? Are these, yeah, okay. Right. After 2 hours, 4. How about 3 hours?
16.
Okay, so it's
Or
1, 2, 4, 8, like that. Okay. And let's double check this with the log conversion. Okay. So I could also say T equals natural log of n divided by natural log of 2. Okay. That's the same thing. Okay. And I can check all these values right here. So what if I do natural log of 1 divided by natural log of 2? that tells me that 0 hours have passed. That's exactly what that says right there. All right, 0, 0. And then what about if I let 2, or the number of amoebas is 2? Then 1 hour has passed. Okay. And then if I plug in 4, I get 2. And then if I plug in 8, I get 3. Yeah. All right. So using the logarithms, I confirm that table right there. All right. So let's plot these points. So the number goes up to 8. So let's go 1, 2, 3, 4, 5, 6, 7, 8. And then the time goes up to 3. So 1, 2, 3. Let's go 0, 1, 2, 3. Start 0 there. All right, and plot these points. So 1, 0 is the point. So if there's 1 amoeba, that means it's just been put in there. Okay. After, well, when you see 2 amoebas, that means that 1 hour has passed. When you see 4 amoebas, that means 2 hours have passed. When you see 8 amoebas, that means 3 hours have passed. Right there. Yeah. Yeah, see, it's going to be a logarithm. Logarithm.
Wow.
All right, you guys good on that?
Yeah.
That's good. All right. Let's skip ahead to 8.2. All right, so 8.2, we basically get more of these ahead here. I do. Let's do number 25 down here. Okay. Again, all the green highlight if you want to see those recorded already. Okay. Recall that the loudness of a sound in decibels. Ooh, right. Hey, here's my decibels. I showed this to you yesterday. Remember that? Okay. So let's do a quick recap again. The concept of this. So right now, just me talking, it's probably pretty close to 60 decibels. Right? Guys, what if you took the number of decibels and you double it to 120 decibels? Okay, show of hands. Would that be twice as loud or no? How many guys see going from 60 to 120 decibels? How many thinks it's twice as loud? Nobody says that. Nobody says that. Guys, 120 decibels is like if you're right next to a jackhammer. You're going to blow your eardrums out. Right? Because this is a log scale. You can see it in the equations right here. So sound pressure, sound intensity, slightly different equations, but they both involve this logarithm. You see it? They both have a log in them? Yeah. Okay, so that's context for this question right here. 25. So they're saying 25. Now, your book is calling this loudness. I was calling it sound intensity level. That probably sounds right. It's 10 times log base 10 of R, where R is the sound's relative intensity. So relative intensity. Okay. So connect this back to the story I was just going over you guys with. If I went from 60 decibels to 120 decibels, okay, maybe I've doubled the quote unquote loudness, because that's how we're quantifying this in decibels. Okay. But the actual intensity, like what's the pressure on your ears, has gone up several orders of magnitude. Right? Several orders of magnitude. Okay. Right, so if the relative intensity of sound is multiplied by 10, okay, so I'll say L new equals 10 times L old. Okay. It's relative, oh, so sorry, R, whoops, guys, what's that? The relative intensity. Okay. Sorry, switch that R, right? That's like saying, suppose there was one person talking, and then you have 10 people talking. Guys, if you have 10 people talking, it's definitely going to sound louder, right? Okay. Oh, yeah.
What's behind the R?
Yeah, here, I'll rewrite this. Okay, so it's R new equals 10 times R old. Okay, so that's what it's supposed to say. Okay. So there was some relative intensity from one person talking. Now we're going to have like 10 people talking. Okay. So how many times louder is it? Well, you could say it should be 10 times the relative intensity. Okay. But our ears sort of perceive loudness on a logarithmic scale. Okay. So we're going to say what's the loudness, but we have to push this through a logarithm. Okay. And it results in 120 decibels. What was the relative intensity of the original sound? So they're also saying L new equals 120 decibels, okay, which is what I was calling the threshold of pain here, right, where your eardrums are about to be torn apart. Right. So that's if you have or maybe it's 1 jackhammer and 10 jackhammers. Maybe that story makes a little more sense. Okay. Right. So you guys go with the premise here. Okay. Here's loudness in decibels as a function of relative intensity, which is the logarithm. Okay. You're saying, hey, instead of having 1 jackhammer, let's have 10 jackhammers. And that's going to bring the loudness up to 120 decibels. Therefore, how many decibels was a single jackhammer? Okay. Well, we're going to find out. So let's go. Okay, so I'm going to use this model right here. Okay. I mean, let's do a system of equations version. Okay. So maybe my new loudness is 120 decibels. And that's from 10 times log base 10 of 10R. Okay, you guys remember I have 10 this is 10 jackhammers going. Okay. Okay. So how many decibels was just a single jackhammer? I'll call it L naught. That's what we're solving for. Okay. Well, it's the same basic equation. So 10 log base 10. Right. But now there's only a single jackhammer. Okay. Okay, so we're gonna say what's the loudness associated with that? Like how many decibels? Okay. You guys get that set up? Okay. Okay. Yeah. Is there any question why I set this up this way? Here, this is really a system. Here, I'll explain it one more time. Because maybe it clicked, maybe it didn't, but we're seeing it. Okay. So here's the model we're using. So loudness in decibels is a log equation based on the relative intensity, maybe in watts or something like that, or pascals, but now they're telling us that if you have 10 jackhammers, that brings the loudness up to 120 decibels. That's what it is. So what's the loudness of a single jackhammer? Okay. Right. Now there's different ways you can solve systems of equations. Guys, could I divide one equation by another equation? Could I do that? Wait, do that. Actually, you know what? Do that. I kind of like the idea because it could cancel out this 10 right here. But the problem is I still have the L and the R. Okay. Let's try a different way. Okay. Let me turn this into an exponential. I think we might be able to make more headway that way. Okay. So I'm going to divide both sides by 10. Okay. So I'll do 12, and that would be bells, basically. Okay. It is log base 10 of 10R. Okay. And then over here, the original loudness divided by 10 is log base 10 of just a single R. Okay. So this is, again, my system. All I did was I divided both sides by 10. Okay. So that I can, next step, convert this into an exponent. So let's do this base 10 to the power of the other side. So are you guys ready for a conversion? Guys, what do you think I'm going to write right here? 10 to the what? 10 to the 12. Okay, so look at this right here. Okay. And that's equal to 10R. Okay. Versus this one, if I do 10 to the L naught over 10, that's equal to just this R right here. Okay. So I converted my logarithms into exponent. So, but it's the same system. Okay. That's it. Okay. Actually, now would be a good opportunity to divide one equation by the other because I can cancel out this R and therefore I can solve for L. Okay. You guys ready to do that? Okay. Let's divide one equation by the other equation. Let's do that. Okay. Guess that. Okay. So next step, I'll have 10 to the 12 divided by 10 to the L over 10 is all equal to, now 10R divided by R itself is 10. Okay, good at that, right? Yeah. Now I really want to get this L. So I'm going to cross multiply this. Well, what is the denominator of a fraction? I get 10 to the 12 equals 10 times 10 to the L over 10. Like that. Right, that okay? Okay. All right. Right. There's a couple ways to handle this. Because if you have, guys, isn't this basically 10 to the 1 times 10 to the something? Can I combine these exponents right here? You guys, how do you combine exponents like this if you multiply and they have common base? What do you do with the exponent? You add on. So you say 10 to the 12 equals 10 to the 1 plus L over 10. That's true, right? Yes, it. Okay. Okay. And now I could take log base 10 to both sides. But all that would do anyway is it would give me this exponent is equal to this exponent. Do you guys see that? Okay, all right, and we're about to finish this off. So 12 is equal to 1 plus L over 10. Subtract 1 from both sides, 11 equals L over 10. Okay, so then times 10, the original loudness was 110 decibels, is what it was. All right, there you go. Guys, I know that was a lot of little steps. Right? Every single step was okay, but kind of long process. Okay? So I'm going to recap the story then. Okay? So go back to the beginning here. Okay? We were given this type expression, right? So loudness in decibels as a function of the relative intensity. Right? Now there's a logarithm set up. Okay? There was one jackhammer producing some original loudness that we had to solve for. And this was the answer, by the way. And then if you multiply by 10, so you get 10 times the number of jackhammers, it brings it up to 120 decibels. So what was the loudness of a single jackhammer? Now again, to jump to the end, the answer ends up being 110 decibels. If you have 110 decibel jackhammer, and then suddenly you have 10 of those, right? It only jumps up to 120 decibels because the logarithms, right? Right. All right. All right, you guys get there? Okay. All right, so what else we got? Ooh, yeah, let's do something here. Okay, so next page. How about
Mr. Griffin,
yeah,
这次不想
oh sound?
Yeah.
All right, so you got.
Okay.
All right, how about number 31? Okay, this will be the last one we do today. Number 31, last one. And then you guys can turn these in and should be easy points. So I have log base 2 of x plus log base 2 of x plus 2 is all equal to log base 2 of 8. Okay, like that. Okay. Now, there's probably more than one way to go about these. But let's see. Okay, we're solving for x, solve for x, solve for x. Okay. So one thing I know I can do is, guys, if I have a log plus another log, let's see, log plus a log. Okay. Do you guys remember this from yesterday? If you have log of a plus log of b, isn't that log of a times b? Isn't that? Okay. Let's try it that way. Okay, so I'll combine these two and make one giant logarithm. I'll go log base 2. And then inside, that's x times x plus 2. Okay, and that's all equal to log base 2 of 8. Perfect. Guess you get next steps. Guys, if log base 2 of something equals log base 2 of something else, what do you know about these inside pieces? Guys, are these the same? They have to be the same thing. They have to be equal. Is that true? Log base 2 of something, log base 2 of something else. The inside part's got to be the same, right? Okay. Could I also expand this out? Guys, can I distribute the x and go x squared plus 2x? Yeah, okay, so that's all equal to 8. Is that okay? Yeah. You can see this is going to become quadratic. I got an x squared, I got an x, I got a constant. So let's get everything over to one side, just like we have for all of these. Okay. So I'll subtract over the 8 and get it set equal to 0. Okay. And see, can I factor that? That looks factorable, doesn't it? Is that factorable? It's not going to factor that. X plus what? X minus what?
X plus 1 and x minus 4.
X plus 4, x minus 2. Right? So let's check with FOIL. First, outside, inside, last. First, x squared. Bing! Outside, negative 2x, inside 4x. That adds up collectively to 2x. Bing! And then 4 times negative 2 is negative 8. Bing! Okay. Because if you were not able to factor that, or if you had like messy numbers that wasn't factorable nicely, could you use the quadratic equation instead? Yeah, you could do that too. Okay. But we're about to get the answer. Because if x is what? the whole thing is 0, or if x is what, the whole thing is 0. X can be what or what? How about positive 2 from here? Or what from here?
-4.
-4? Okay. Okay, so there's one last trick with this. And they give you a hint here. It says check for extraneous solutions. It might be the case that both of these don't work. Maybe only one does. Let's go back to the original statement. Guys, can you take a log of a negative number? Can you do that? Log of a negative?
No.
No. Guys, here's a basic log curve. Okay. That red line doesn't cross the y-axis. It's only positives. Right? You only take logs of positives. Therefore, guys, which answer do I have to throw out? Yeah, it's -4. Okay. So there's only one true answer, and that's x is 2. And that one will succeed. So if you want to, of course, you can take that answer, plug it back to the original statement, and it'll give you a true statement. All right. So guys, double check, make sure your name is on your notes. Turn your notes into the grade tray, and I will give you guys points.